Okay, I think we'll continue now. So we'll look at the next lesson. I don't know why I have an S in there. Ideal gas law. I don't know if you've noticed this, but in Ireland when people speak, they sometimes put extra S sounds at the end of words. Have you noticed this? No? What's the name of the bookshop, the big bookshop in the middle of the city centre on O'Connell Street? Yeah, how do you spell that? Yeah, but if you ask any Irish person to say this, they'll always say Eason's with an extra S at the end. So sometimes I accidentally do things silly like this, put extra S's at the end of things that I don't need to. So that should be just ideal gas law, not ideal gas laws. So just don't write the S. Ideal gas law. You might have done this law in chemistry.
Yeah.
This year, I mean. Yeah, you've done this already. What?
Yeah.
Recently? How recent? Just before the break. Super. Okay. Right, so a little bit before we start. A lot of it. Boyles Law. Does anybody know Boyles Law? I'm sure somebody might know Boyles Law. It's the one with volume. Well, yeah. Go on. Yeah. You can give it to me as a formula if you know it, or just as a statement. I thought you did. Yeah, there's two ways to state it, yeah. So the first way to state it is that P is proportional to 1 over V. So if you make the V bigger, then the P for the gas will become smaller, or vice versa. If you make the V smaller, then the P becomes bigger. The way you stated it would actually be to say PV equals constant, or the other way to state it is P1V1 equals P2V2. So you actually have a few ways to state Boyle's law. This is probably the easiest way. Although there's a condition you must include with this. P is proportional to 1 over V, yeah? Yeah, provided the mass and the temperature is held constant. Mathematically, P proportional to 1 over V, or PV equals a constant, as you said it. Simply put, Boyle noticed that if the volume is halved, then the pressure is doubled. It's kind of the simple way to put it, or vice versa. What's so funny? Huh? I don't. Is there something dirty on the screen? No. Huh? What's wrong with you?
She's hungry.
She's going crazy with hunger, is it? Did you have lunch? You had lunch. What did you have for lunch?
Bread,
Yeah?
apple, banana, orange, chicken.
And you're hungry?
And
Did you have breakfast?
yes,
What did you have for breakfast?
you.
Yeah, okay. So why are you so hungry? Is it the cold weather?
It was really hungry.
Ah, you had a good holiday then.
I'm hungry.
So what you're saying is you got used to eating a lot and doing little. Yes, okay. No, I understand this. Today I already had 4 cookies and 2 chocolate bars. Terrible. I do actually. I have chocolates in the office I can give you. I don't have any on me now, which is what you really need. Okay, did you write this down? What country is Boyle from? Does anyone know? Now come on, think about it. Why would I be asking you? Very good, yeah.
Oh my god, Aaron.
Yes, yeah. Not only is he from Ireland, he's actually buried in the church around the corner. You can actually visit his grave if you like. Yeah. I'll show you where. St. Patrick's, you know? The big one, yeah.
The church.
The big one, yeah. So here we are here. Yeah. D-I-S. Come out here, go down to the lights, go down here for a little bit, a few minutes, and maybe after about 10 minutes, the big church on this side. And he's somewhere in here. I don't know where because I haven't been, but he's buried in there somewhere. Yeah. Yeah, it sounds like a physics field trip, doesn't it? Yeah. So yeah, you could pass him every day you go home, and you didn't even know it. So he's not that far away, actually. So that's Boyle. I don't remember which part of Ireland he was from. I don't think it was Dublin. I'm not sure. It might have been somewhere outside Dublin. Anyway, that's Boyle's Law. Yes, you know that now. Yes, yeah. Okay, so this is not the only relationship. There are other relationships. So you might not be surprised to know that temperature and pressure are related. What do you think the relationship might be between temperature and pressure? If you picture how the two behave, what might be the relationship? Yeah, directly proportional. Because you know from day-to-day experience that if the temperature is increased, then the pressure will increase too, until kaboom, something explodes. And there's a very, very interesting graph, a very important graph you can make here, which I will draw for you and talk about. So you want to include this. So let's just say here, this is, come on, this again is pressure, and we'll measure that in pascals. And this here is temperature, and we'll measure it in Celsius. So let's take a gas. It doesn't matter what gas it is. We'll put some gas. We'll put some gas in a container. We'll fill it up, and we'll measure the pressure, and we'll measure the temperature. Okay, and we'll change the temperature. We'll heat the gas up, and we'll see the different pressures that we get. So we measure a temperature and a pressure. Then we increase the temperature and measure the pressure again. And what type of graph do we get? Well, no surprise, we get a straight line. So let's imagine that this perhaps is the graph you get for something like oxygen. You increase the temperature, you increase the pressure. And let's say we do the experiment again, but maybe this time with nitrogen. So we increase the temperature, and then we get the pressure that increases as well. And we do it again for some other gas, maybe, I don't know, helium, hydrogen, whatever. What was noticed when this was done is it doesn't matter what gas you study, if you were to continue the line back, they always meet at one common point here. And this is quite interesting because it kind of makes it seem like everything here is impossible because the graph will always end here. And this value is minus 273 Celsius. So it was Kelvin who discovered this, that no matter what the gas, we cannot go past this point on the graph. What I really like about this graph is that you don't actually need any values here. You can just use the values at room temperature. But by using a graph and a bit of logic, you can see that, oh, there's a point here where these all meet, and it's kind of the end of the road. So Kelvin's idea was that this is the absolute zero. This is the smallest temperature you can have. You cannot have temperature less than this 273.15. This is absolutely it. So this is, regardless if it's a gas, it's actually true for every material. It can't be less than 273. So because of this simple experiment, it gives us this idea of what we call absolute zero, which is the lowest possible temperature any material can be at. So that's the definition of absolute zero. So you should write that down. What's that?
The absolute zero is minus 273.5 degrees.
0.15 degrees Celsius. Yeah. Continue. So this actually gave us the idea that maybe instead of using Celsius, we should use a different unit, so that the value begins at 0, which is minus 273 Celsius. So the idea is we have this thing called the Kelvin, which is actually the same as the Celsius, with one small difference. We increase it by 273.15 units. That is, the temperature in Kelvin is the temperature in Celsius plus 273.15. This means in Kelvin, we always begin at 0. We cannot have negative values in the Kelvin scale. By using Kelvin, the temperature is always positive. Formally, so the formal definition of the Kelvin in a moment, but first write down this formula. Well, I mean, you know this formula from chemistry, don't you? What value do you use in chemistry? Do you use 273.15 or 273 or 273? Continue. Yeah. So formally, what is the Kelvin? So the formal definition of the Kelvin is a scale of temperature with absolute zero at 0 Kelvin. So the Kelvin uses a scale of temperature that puts 0 Kelvin as the beginning, absolute zero, and then the triple point of water as 273.16, and that actually is a 16. Now, the triple point of water isn't really something on this course. The triple point of water is a special temperature of water. It's roughly equal to the temperature water freezes at, but it's not quite that, because it's actually 0.01 Kelvin above this, but roughly speaking, the triple point of water is the same thing as the freezing point of water. So the Kelvin scale is a scale of temperature that uses 0 Kelvin as the beginning, and the triple point of water as 273.16 Kelvin. It's roughly speaking the freezing point of water, but technically it's not, because it's actually 0.01 Celsius. Something very interesting can happen with water at this exact temperature. Yeah. If the water is at this temperature, 0.01 Celsius, at the right pressure, it's possible for the water to be a solid, liquid and gas at the same time. Which definitely means we should have a YouTube video of that later. We'll look at triple point a little bit later, okay? Continue.
Should we remember it?
This is the definition in the exam for Kelvin if they ask you. Yeah. I'm sorry. How many marks would be this definition in the exam? 2 marks. You get 1 mark for stating that 0 Kelvin is absolute zero, and 1 mark for stating that 273.16 is the triple point of water.
We should remember it.
Yeah. It's okay because this value is on your calculator, and this value is only 1/100th of a Kelvin more than this value. Can you see, just a 6 instead of a 5? Yeah. Oh wait, you don't have this calculator. Well, you should have this calculator. This is on the calculator, isn't it? I think so. Give me the lid. I don't know which letter it could be. I'm looking for something. If I was to guess, I would guess. No, what? Type in 37. Shift 7, 37. What you get?
370.
No, that's not it. I don't know. Try. No, don't know. It's in the formula book anyway. The formula book. Okay, continue.
But the formula book will have the 2 numbers too.
No, I think the formula book just has this number. How do we count in physics? I know this seems like a simple question, but I mean, when we count, we do use a unit. That is, imagine we had some water. We do not say we have 10 to the 23 molecules of H2O. I mean, we could say we have 10 to the 23 molecules of H2O. But we need to use a unit to count, because in physics when we count something, the numbers will be very big. So what unit could we use? Well, maybe we could use mega, maybe we could use giga. But even mega and giga will be too small, because mega is 10 to the 6, giga 10 to the 9, tera 10 to the 12. So even these are too small. For example, bakers. Bakers count in 13s. So bakers would count in groups of 13. Farmers, they count in groups of 12. Did you know this? No? I don't know if it's a Western thing. When you go to the bakery back home, does the baker not sell things in groups of 13, like 13 buns or no? Well, when you buy eggs, how many eggs are in a carton of eggs? 12, yeah, so 12 eggs. So you can see that's the farmers, they count in 12s. So there's 12 eggs in a carton. Same for your home country? Yeah, 12 eggs?
No, 13.
No, it's not 13.
How does it look like?
Yeah, exactly, yeah.
You said it's 32. We have 12 and 13. We've got 15, I think we have.
15, that's not right to talk. Eggs go 6, 12, 18,
No, I've got word 20.
and 24.
No, 13.
30? 30 we can have, yeah.
Oh, it's a square.
Yeah, I'll check next time. Anyways, my point is, farmers count in 12, bakers count in 13. In physics, we count in units bigger than 10 and 13, because that's too small. We use something called Avogadro's constant. Yes. Avogadro's constant. Ah, no, you know this from chemistry. Now, a mole of something, which we can count, it doesn't matter what it is, it could be molecules, cups of coffee, stars, whatever, is 1 Avogadro's constant of that something. And how much is the Avogadro's constant of that something? It's, yeah, there you go, 6.02 times 10 to 23. And here's a little fact for you. Who first estimated the value of Avogadro's constant? I think the first estimate of Avogadro's constant, I think, was maybe 6 times 10 to the 23. And who estimated that? You would think it would be Avogadro, considering it's named after him. But in fact it was Einstein who had this estimate.
Einstein.
Yeah.
Newton?
Not Newton, no. So why it's called Avogadro and not Einstein, I think it's a bit unfair. It should really be called Einstein's constant, since he had the first estimate of its value. And he was pretty close. He said 6 times 10 to the 23. It's not that bad. Oh, you used 6, not even 6.02. Okay. Yeah. Okay, great. So you're using Einstein's original value then. Did you write this value down? This is called a mole. So in physics we count in moles. So we can have 1 mole of something, 1.5 moles of something, whatever. We count in moles. Yep. Continue? Okay. Hang in there. Are you guys still talking about the eggs?
Egg.
You're not happy with her number, is it?
I just feel
Hungry. Do you know the word in English for 12? 12 eggs? Dozen, yeah. And do you know the in English for 13? Like 13 cakes? No. Yeah, baker's dozen.
Baker.
Yeah, dozen for fun. Dozen is 12, baker's dozen is 13. Yeah. The idea is the baker gives you 1 free. So you pay for 12 and you get 13. That's the idea. Okay. Yeah. Clearly you're not buying cakes in the dozen. You must be only buying your cakes 1 by 1, is it? If you buy 12 cakes, you might get 1 free. You should try that in a bakery sometime. So, if I have 1 mole of H2O, or 1 mole of cups of coffee, or 1 mole of stars, then I have 6 times 10 to the 23 molecules of H2O, cups of coffee, or stars. It's just a way to count. That's all it is. Okay, so imagine I have 1 mole of cups of coffee. That's a lot of coffee, right? What would the mass be? So I want you to calculate the mass of this. Now, I didn't give you any information, so I just want you to roughly calculate it. Think about how big a cup of coffee is, and calculate the mass, please. A cup of coffee is not a litre, okay? Be realistic. Half a litre is still too big. This is a 1/4 litre. Yeah. So what would be the mass of this?
3.
With the cup?
3 grams.
Yeah, how many grams?
3 grams.
3 grams? 3 grams? Really? No. No. Come on.
9 grams.
If this was a cup of water of 250 milliliters, what would its mass be? 250 grams. Because 1 milliliter of water is 1 gram in mass, yeah? I know, but coffee is mostly just water with a few coffee beans. Anyways, this is about 250 grams. Okay, it's about 250 grams. So calculate, please, the mass of a mole of these. Now that's a lot of them. It's a lot. So you should have an answer like, what did you get?
1.5055.
10 to the 23. Yeah. You should have something that's about 1.5 times 10 to the 23 kilograms. That's huge, isn't it? It's huge. 23. So, no, 20. Wait, hang on. 250 grams is 0.25 kilograms. So it's about 1.5 times 10 to the 23 kilograms. Yeah, no, you can use, it is usual to use grams, but there's no, it's not like I have to use, like if I asked you what's the mass of 12 cakes, you don't have to use grams or kilograms, you can use whatever unit you want. So if I said what's the mass of a mole of cups of coffee, you can use anything. Yeah. But you're right, it is more usual to measure it in grams. But maybe not for this question because it's so big. It's huge. The point in this example is we call this the molar mass. The molar mass is just, the molar mass of a material is the mass of one mole of it. So for cups of coffee, this is quite a big number because if you have a lot of these, then the mass will be quite big. But for something like a H2O molecule, then having a mole of H2O isn't that much actually, and its mass could be measured in grams, like, I can't remember, it's like 30 grams or something for a mole of H2O. So it's common to use grams here. Okay, for example, the molar mass of H2O, does anyone actually know what it is off the top of their heads?
18.
Yeah, actually, is it 18? So if you have a mole of H2O, you actually have about 18 grams of H2O. Okay, so can you write this definition down, please? You probably did this in chemistry too, right? Yeah.
You know what don't we ask this definition? In exam, we don't really ask this definition.
In which exam? Physics or chemistry? I can check now for you. 1 second, Bruce. I'll check. Hang on.
Actually, it's okay.
Ah! Too late.
No.
Understand that 1 mole of the substance has a mass equal to the... Yeah, no, that's okay. No, they should not ask you the definition of molar mass in the physics exam, although I thought perhaps it could be a question in the chemistry exam. Okay, let me just go back to... No, I'm only 1 slide away. Whoops, 2 slides away. 3 slides away. Okay. So, some important notation now. We use the letter big N to represent the number of molecules, and we use the letter small n to represent the number of moles. Is this the same as your chemistry class? Do you use small n for moles and big N for molecules? No? It's the other way? Think carefully.
Only small n.
Ah, you don't... Well, what letter do you use if your teacher asks you for the number of molecules?
Just number.
Number of
Just number.
Oh, you have to write a number of particles like this? That's horrendous. Oh. Yeah, I'm just going to write big N. Big N is for number of molecules, and small n is for number of moles. Don't mix them up. How can you remember the difference? Quite simple. Quite simple. The big N is going to be bigger than the small n. So small n is number of moles. This will be a small number. Big N is number of molecules, and this will be a big number. Big N for big number, small n for small number. In fact, you can relate the big N and the small n quite simply by this formula. The number of molecules equals the number of moles multiplied by Avogadro's number. Again, this is something you saw in chemistry. Yeah? Big N is bigger than small n. That's how you can remember. Okay, continue?
Yeah.
Yep. So, here is a very, very quick question that should be easy peasy for you chemistry students. 1 litre of water is at room temperature and the molar mass of H2O is 18 grams a mole. How many moles of H2O are in 1 litre of water? Okay, calculate these 4 parts. They should be quite straightforward, I hope. 2 minutes maximum. It's so easy, it's hard. Do you need a little hint? No, okay, no help. No help. Boom. Okay, got the first one? So how do I get the answer for the first one? How many moles of H2O are there? What? Yeah, what do I divide?
One over 24.5.
No. Now what do I calculate? How do I get the answer? Oh, this question is so easy it's confused you, hasn't it?
How many grams?
Exactly. I thought this was knowledge you had. 1,000. Yeah, so what do I do first there? You seem to have the idea. So
1,000 over 18.
that's it, yeah. 1,000 over 18.01528, for example. So, how many moles of H2O are there? 55.5 moles. How many molecules of H2O are there? Yeah, we multiply this by Avogadro's number. That's how many molecules of H2O there are in a litre of water. Yeah. Now, how many oxygen atoms are in 1 litre of water? Oh, no, not necessary. The answer is this. Because in every molecule of H2O there is 1 oxygen atom. Which means if there's this many molecules of H2O, then there's also this many atoms of oxygen, because each molecule has 1 oxygen atom. The last one though is different. How many hydrogen atoms are there? Double this, yeah. So this is how many hydrogen atoms are in a litre of water. Yeah. Basic chemistry. Is it really? Okay, well, you have a head start on it then. Continue? Yeah? Okay. Let's go back to Boyle's Law for a moment. So Boyle said, Boyle said pressure is proportional to 1 over volume. But there's other formulas too. We know that pressure is proportional to temperature. We talked about that. Also, volume is proportional to the number of molecules. If you have twice as many molecules, then you will have twice the volume. Pressure is also proportional to the number of molecules. Now, this one here, again, we have to think back to our model. The pressure is caused by the molecules hitting the wall and changing their direction. If you have twice as many collisions with the wall, then you have twice as much change in momentum, twice as much force, and so twice as much pressure. Volume is proportional to temperature. If you increase the temperature, then the volume increases. And this is usually true, except we know for some things where this is not true, like water between 0 and 4. It seems like all of these are coming from one formula that relates all of these together. And in fact, if you study each of these carefully and think about their relationships, you can actually arrive at this formula, called the ideal gas law formula, which is what you did in chemistry, and I'm going to do it again now with you, is that PV equals nRT if we use moles, and R is a constant called the ideal gas law constant. And you probably know the value of this constant, do you?
Yeah.
What is it?
8.31.
Yeah, 8.31. What's the unit? Let's have a quick calculation of the unit.
PAM cube over more.
Oh, don't worry so much about those bullet points. They were just all there for the reason of giving you the ideal gas law, which is what you need. If you need me to flash it back up there for a second, that was there. So PV equals nRT, I forgot what letter I'm using, small n, nRT, then R is equal to PV over RT. What am I doing? Sorry. Hang on. The problem is, when you get used to waking up at 12 o'clock and then you have to wake up at 6:30 for work, your brain is not right for the rest of the day. R is PV over NT. So the unit for R will be, let's see, pressure is at newtons per meter squared, and volume is meter cubed, and N is mole, and temperature is Kelvin. So it'll be Newton meters per mole per Kelvin. And actually Newton meter is another unit. What's Newton meter? It's actually a joule. Yeah, so you could actually write as joule per mole per Kelvin. I don't know what you use in chemistry, if you use a unit, or do you just say 8.31? What unit do you use? Do you know? PA? What the heck is that? Pascal?
Yeah, Pascal m cube over mole.
Ah.
Yeah,
Oh, I see. You say Pascal m cubed over mole Kelvin, because this is also Pascal. Oh yeah, okay. Ugly. Because I can simplify it down to just this: joule per mole per Kelvin. Yeah, but this is totally fine as well. This is fine, no problems there. Anyway, back to the formula. That's if you use moles, but of course if you use molecules, then we actually use a different letter which we call K, and that K has a different value. So, let's see what's happening here. You probably use this formula, PV equals nRT, in chemistry, right? And N is the number of moles. Now, let's see what happens if I multiply both sides by Avogadro's number. So, N times Avogadro's number, what does that give me? Big N, yeah, the number of molecules, isn't it? Big N or T. Now, if I just divide by Avogadro's number, then this is the formula using molecules instead of moles. The only difference is the constant, instead of being R, is R over Na. And this is what we're actually calling the K in the second formula. So it's not like the K is something new or something special. The K is actually just R divided by Avogadro's number. So it's not particularly special. We check the dimensions. Dividing, we can see that it's the same formula, just with a different constant if we're using different units. We call the R the ideal gas law constant, and the K, in fact, even though it's nearly the same thing, it actually gets a new name. We call the K the Boltzmann Constant. Even though all the Boltzmann Constant is just the ideal gas law constant divided by the Avogadro constant, we get what's called the Boltzmann Constant. So Boltzmann gets a constant named after him, even though it's not anything special. they're actually the same thing, just with different units. Like, I mean, there isn't really any difference here. So why do we need two constants? Why bother with two formulas with two constants when the only difference between here and here is Avogadro's number? I don't know. You'll need to ask a chemist. But anyways, I'll give you the values. Ideal gas law is 8.31 constant, and the Boltzmann constant, which is just this divided by Avogadro's number, will be 1.38 times 10 to the minus 23 joules per Kelvin. Per molecule, if you want to be particular about it. Yeah. Got that? Finally, note, we always use Kelvin for these formulas. A classic, stupid exam student mistake is to use Celsius. Don't let that be you. Okay? Always use Kelvin for this formula, but you should know that from chemistry as well, right? You use Kelvin in chemistry for these ones. Huh? Yeah. Well, you have a test tomorrow in chemistry. I thought you said you have a test.
We have the afternoon free, yeah?
Oh, yeah, we have
Huh?
students.
We don't have class.
I thought that was a chemistry test.
Yeah, we should be having tomorrow, but the new timetable doesn't say there's chemistry classes.
Oh, then I guess you don't. Anyways, continue here.
Maybe tomorrow class.
Just go with the new timetable.
So we leave?
Oh.
If there's no scheduled chemistry class, it can be.
Yeah. If the timetable says you're free, then you're free.
Yeah.
Yeah.
Okay.
Chemistry.
All right. Here are some molar mass values you'll need for the questions. Okay. So the first one is liquid water. It's about 18 grams. And you should also know the structure. It's 2 hydrogen and 1 oxygen at the molecule of H2O. So if you can write this table down.
Why did you have to write triangular question?
Yeah, good idea. Okay, the next one is carbon dioxide, CO2. It's 44 grams a mole, and it's 1 carbon and 2 oxygen. Okay, got that? The next one is hydrogen gas. It's about 2 grams a mole, and its structure is H2. No. I mean, you need these values for your homework, but in the exam they've provided. Okay, the next one is helium, which is about 4 grams a mole, and it's just 1 helium atom is its structure. The next one is oxygen. Oxygen is nearly 32 grams a mole, and its structure is O2. Okay, got that? Next one, and last one, is nitrogen gas, which is about 28 grams a mole, and its structure is 2 nitrogen atoms, N2. Now, you notice, and you know this from chemistry, Hydrogen, oxygen and nitrogen are interesting because they form pairs. Unlike helium, which can exist as a single atom, if you have a gas of nitrogen, oxygen or hydrogen, they form pairs. How many atoms have this property that they form pairs, like nitrogen, oxygen, hydrogen? Do you know this one? Huh? Yeah, but how many? Is my question. Yeah, how many gases, how many atoms have this property that when they're in gas form, they form these bonds of pairs of two, like N2O2, H2. How many of these pairings are there? No, there's at least 3 because I just gave 3 examples. So, that sounds like a wild guess and it's wrong. No, you don't know. There's 7. There's 7 atoms that behave like this, and they're called the diatomic atoms. The diatomic atoms are the atoms that form in pairs. N2O2, H2. There's 7 of them. Did you not do this in chemistry? The diatomic atoms, these 7 atoms. No, are you sure? Okay. Well, it's not really part of the physics, but it will come up in chemistry if you want to write this word down to look up. Diatomic. And it's things like H2, N2, what was the other one I said? O2. I can't remember, there's 7 of them altogether. I don't... No, not CO2, just a single... Cl2, okay, yeah. Cl2. You think you know the 7 of them? How do you know the 7 of them, but you don't know the name of the 7 of them? You did? Did you? You see, you need to be louder. That's it. Yeah. You need to be like this guy. Yeah. See, I can always hear him. Okay, so you did know the word diatomic then. Okay, yeah. And you knew there were 7 of them then. Okay, well, so you learned something then. That's good. Okay. This isn't really something in the physics. This is more in your chemistry syllabus. Okay. Do you have this table? Yeah. So this example is very long. There isn't time to do it now. So we'll start the next class with this. That clock's actually a little bit slow. We'll start the class next time with this example. When is our next class? There's only the one example to do. Wait. If you want, I will do this in the next class, but since you've done this in chemistry, and since you said you have a chemistry test in this topic, didn't that's what someone said? Yeah. I don't think it would be a bad idea to take a picture of this and just to try to see if you can do it before I do it. Might be an idea. Because, to be honest, I think this is probably harder than what you might do in chemistry. So if you can do this one, it's a good revision for you. And if you have trouble with it, I'm sure your chemistry teacher would be delighted to help you with this one.
What time is it?
Okay. Can I close this?
Mm-hmm.